So we've seen that the inner product allows us to measure angles between vectors, and that's really important. So we need to know a lot of things about the inner product because of this. So we have the following theorem, and this theorem is just a big catch-all for a bunch of different facts, and all the individual facts are kind of easy to prove, but it's nice to put them all into one theorem. So let U, V, and W be in Euclidean n-dimensional space. Let R be a scalar, so a scalar is just a real number. Then, first of all, we have that U inner product with V is equal to V inner product with U. And this is often called symmetry of the inner product. And this fact is real simple. If you expand it out and then just commute everything, right? So commute all the individual products, then you get this side, right? So this follows by commutativity. In R1. So B, the next thing is that U dotted with V plus W is equal to U dotted with V plus U dotted with W. And we'll say that this is linearity, right? So whenever we can do this, whenever we can take a sum and pass it through another operation, we call that linearity. So this will be called linearity. And this follows just by using the distributive property. In R1, and we do it n times, right, for each product in this sum. Part C is that we have, if we take U and dot it with R times V, well, this is equal to R times U dotted with V. And it's also equal to RU dotted with V. And this follows by commutativity. And the last one you get essentially by associativity. In R1, of course. The next fact is kind of interesting. So that we have that U dotted with U, right? So the same vector dotted with itself is greater than or equal to 0. And this is true since, if I take squares of everything, it's always greater than or equal to 0. And if I sum a bunch of squares that are greater than or equal to 0, then I get something that's greater than or equal to 0. And also we can kind of see this from the cosine definition, right? The cosine between U and U is going to be 1 because the angle is 0, right? Cosine of 0 is 1. So this will be positive because it'll end up being a squared length. And we'll talk about that in just a second. E, we have that U dotted with U equaling 0 implies U is equal to 0, right? So, of course, if U is equal to 0, the 0 vector, right? So the vector with all entries 0, then of course this is true. This gives us the converse, right? And the whole reason is, well, we can prove the contrapositive of this statement really quickly, right? If U is not equal to 0, right, so we have some entry that's non-zero, and then over here we'll have a sum of a bunch of things that eventually we'll have a non-zero entry in, and then that sum will have to be strictly greater than 0, right? So that just follows by the contrapositive, which is easy to show. F, we have that U plus V dotted with U plus V again is equal to U dot U plus 2u dot v, and you can derive this little fact using all the other facts that we've gathered, right? You can just use this guy and symmetry, and you're good to go, basically. So this is kind of a nice little formula. You can work it out. It's not a problem. And so we mentioned this fact that the magnitude of u is actually equal to the square root of u dotted with u. And this follows from C, essentially. Well, no, this doesn't follow from C. That's crazy talk. You can see this just by looking at the definition, really, right? So this fact, along with C, though, right? So along with C, this gives us the following fact, right? So let's take RU and take the length of it. So I multiplied R times U, and I want to look at the length, and I want a simple way to figure out what that is. Well, this is the square root of then RU dotted with RU. And I use part C twice, and this will give me square root R squared times U dotted with U. Right, but this is then equal to square root R squared times the square root of U dotted with U. And each of these is equal to, the first one is just the absolute value of R, and the second one is just the norm of U. So this is a nice little formula that our length will obey, right? And it makes sense, right? If we multiply everything by a number, then length should scale by that number.